we have a simple mechanical system that we would like to analyze and do simulation for finding the position of this mass at every instant of time. And so I'm going to choose this simple example in here to illustrate how to do that simulation using the block diagram method. The very first thing that we have to do is to find the free body diagram. And what does that mean? It means that we make an isolated diagram of each one of the masses, and we look as to what forces are applied on them, and based on that we write the differential equations. So in this case, let's just go and do just that and draw the mass in here and in here, and then we'll draw the different forces that are applied on it. So in here you go, and let's go over here, and we see this is the force that is to the right hand side over here. We're going to call this F. And then we have, if we pull it to the right and we measure the displacement X, this is going to be the positive direction, to the right. Negative would be to the left. So in this particular case, we have this force to the right, and if we do that, you see the other two are going to oppose this. So this is going to be K times X this way, and the other one is going to be B times X dot also to the left. So in this, this is our free body diagram. Okay. If we go on to the next step, we could put in here number 2. If we could do that, and we say step number 2 is going to be apply, you say, apply Newton's second law of motion. What does it mean? It means that that we apply second Newton's law of motion, hopefully be able to move this down. Oops, but not that way. We didn't want to mess, oh, we messed this whole thing up. Oh, I see. Is making part of the system at the top, and we don't really want that. So why don't we make another one over here? Yeah, there it is. So we're going to put apply Newton's second law of motion. Very good. And in that regards, we can move it over here. What does Newton's second law of motion mean? It means that if we do the summation of forces equals to the rate of change of angular momentum, we can express it in the form of a differential equation, you know. So basically what this is saying is that the summation of the forces equals to mass times acceleration. That's another way of saying this. So we have F, then minus K times X minus B times X dot is going to be equal to mx double dot, like that. Yeah? That's what this means. I suggest that you leave it in this form because it's easy to generate the block diagram. So if we could go on and do on the next one, I would say this number 3. Let me put it here because we have a space, and you say number 3 is going to be say convert the differential equation into a descriptive diagram, block diagram. Okay, so if this is the case, what I would do is I would begin describing the summation here, and you say this, and you say, okay, I describe the summation here as, see, this is the summation point. On one side, right here, I have an input of this force F, yeah, with positive sign. I have an input of this force minus k times x. I have an input of this force minus b times x dot. This is equal to mx double dot. So here's the description of this little picture is that of this equation. So the summation of these terms is expressed in this summation point here, and this is the result. So f comes in here, this minus x minus b equals, this is the result. So if you start like this, chances are that you will have an easy time doing this block diagram. So in here you have, this is 1 over m. If you do this, you would end up with just x double dot, right, on this side. And in here, if you integrate this, 1 over s, and this is x dot, right, if you integrate it once. And if you integrate it another time, this 1 over s would become x. And in here we can, of course, put our scope so that we can see it. And in here you will have, this is x dot. You see, once you have done this, the completion of the block diagram falls from just looking at it, because the signal is b times x dot, but see, this is x dot. So to be able to produce that, all you would have to do is to do it multiply by b, and then you have it like this, see? And this other one, k times x, you would have to do the very same thing. So in here you have a situation where this is k, and then this would join this way, and there's your complete block diagram that you can put into Simulink now. So I think this is the description that we need to do this block diagram. So 3 major steps. One is to consider the free body diagram, apply the Newton's second law of motion, and from that do a graphical description of that equation. So now we turn our attention to entering this diagram into Simulink. What I am going to do is to perhaps reduce it in size a little bit in here, so we can actually see it in here. These are the advantages of doing it all on the computer, because not only we can write, but we also can run software at the same time and relate both the writing and the software. So this is perfect setup. So in here we're going to run MATLAB, and since you know that Simulink is a toolbox of MATLAB, then we run Simulink and we can actually do this block diagram. Okay, so we just type Simulink in there, and it's going to start and give us some options on how to draw this block diagram. Simulink is made for this kind of block diagrams. So all we have to do right now is to wait for a little bit to come up, and then we'll be all set. As it goes with software, it always takes longer when you are trying to show it to somebody. But there you go. So and here we go, commonly used blocks. That's what I would suggest that we do. And this one we can move it, and here we can actually reduce it a little more, because that's all we need. Yeah, see? You basically need this. And in here you have the Simulink different different blocks that you can use for drawing this. We need a picture for the we need a picture for we need a space rather for drawing this picture. So in here this one right here is this element, so we'll bring it over here. We have these gains, we have like 3 of this, so you could actually bring them, drag them like I'm doing, or you could actually duplicate the ones you bring one in. We need 2 of these integrating blocks in here, and then we also need the summation point in here. We need this, and we need one of the scopes. This is basically what we have on the top right here. See, and so you have this summation point. The only thing about the summation point is we have 2 of these, one is plus, but then we have 2 negatives. So we need to make it a little bigger so that it's clear what we're doing. So let's just move it like that. So line them up so that they would look nice. And here we connect this input in here. In Simulink, if you click the first element and then hold the control key and click the second one, it will actually connect, see? So you can do this fairly quickly. This one's, we don't have them in the right direction, so they need to be inverted. If you do a control I, it actually changes the direction of those. This right here, it was 1 over m like this, yeah, and then you had the other 2 is, this was of course this was, what did we say, this is b, right? And the other one was k, so let's just do that. And right here was x, and this other, on this other end we're going to connect it, this x dot, and this one was for x, and then we connect it to this one. And see what happened now? We have actually produced this block diagram on the left hand side is exactly what we had in mind to do this. This one in here we called it F, so we should put it in there. Now this program is not going to run, this graph is not going to run unless I give it some numbers. Alright, so I am going to bring up the MATLAB window, this prompting here, and show you that. Perhaps I'll bring it up here in this corner. Let's see, in here, like that. And I am going to give the value. For example, I'll say f is equal to 10, yeah, the input, and then you have the b is going to be equal to 2. I would say k, we need some k is equal to 30, like that. Just some numbers that may produce. So an m is going to be, oh, I think we did say m already. Not yet, m2, and then b, and we did k, and then f we already did also. So yeah, so why don't we, and here we click on this, and now we can actually run the simulation. I think we click it twice and we shouldn't. And so right here I can actually go to this and run it. Let's see how it goes. Hopefully we didn't make any mistakes, and we should see something, and we actually don't. What happened here? This was the one for here, wasn't it? Oh no, it was the other one. So this is the simulation that we see here. And so this is the scope, and we see the position of the mass at every instant of time. If we look at the system, we could take a look at the physical system as we see it over here. This is the simulation of the system you see on the left, and the position of the mass as we have started at time 0 and do it for the first 10 seconds of the simulation. And that is the way we do it for the mechanical system.